Good afternoon. Last class we were discussing the phase diagram of a pure substance in relationship to the properties of pure substances, and where we ended is the temperature entropy plot in course of phase change of a pure substance, and we arrived at this diagram where we stopped last class. So you see again that TS, the temperature and specific entropy, the plot is like this, that this is the vapor dome. Typically these are the saturated liquid lines for boiling or vaporization. This is the locus of point force, which we designated as point 4, the saturated liquid state of saturated liquid for vaporization. Similarly, this is the, what is this? This is the locus of saturated vapor points, that means this is known as vapor line, and this is similarly the saturated liquid line for solidification, and this is the saturated solid line for melting. And these red lines, these are the constant pressure lines. One thing we have appreciated, that a constant pressure line looks like this, that means at constant pressure, if temperature increases, entropy increases during the sensible heating part of a substance. This is the vapor phase, the gas phase, this is the liquid phase, this is the solid phase. While in course of phase change, both pressure and temperature remains constant. So a temperature pressure line runs parallel to the s-axis, because T is the ordinate, that means it becomes constant temperature also. And similarly, this is the triple point line, which will come afterwards. This thing is like this. This is the figure for phase diagram in TS plot. And one thing is that this saturated liquid line, we are not much interested on this part, we are interested on liquid and liquid vapor. So the saturated liquid line for vaporization only heals towards the right. That is because at higher pressures, when the pressure is increased, the saturation temperature is increased, and it takes more heat. Therefore, the entropy content in it, in the system, is much more. Therefore, the line heals towards the right. For an example, if this is an 1 atmospheric pressure line, so this is for water 100 degrees Celsius. If this is a 5 atmospheric pressure line, then this temperature may be something around 150 degrees Celsius. So water has to be heated to 150 degrees Celsius, so that the entropy is more. But here the saturated vapor line healing towards left in the similar way as it happened in case of PV diagram. This is because that entropy, that means here what happens, the entropy is lower here compared to here. Then you can ask me, that though the temperature is higher here, why entropy is lower? That is because at this higher pressure and temperature, the latent heat, which is the difference between the enthalpy at this point and this point, which we will again explain in HS diagram, latent heat is less. Just again I am giving an example, that if it is 100 degrees Celsius water, if this line is an 1 atmospheric pressure line, then this is 100 degrees Celsius vapor. So difference in enthalpy between this and this is the latent heat. That means the entropy changes because of the latent disabsorption. The latent heat is taken at the constant temperature. When we change the pressure, for example at 5 atmospheric pressure, 10 atmospheric pressure, let us consider 5 atmospheric pressure, probably the temperature is 130 degrees Celsius or 140 degrees Celsius, exact value I cannot tell you recalling. So at higher temperature this point is there, but at the same time the latent heat of vaporization reduces as you go on increasing the pressure. So the heat which is given to vaporize this liquid to the vapor is less, so that the change in entropy is less, so that the entropy, absolute entropy, is decreasing as we go on increasing the pressure. That is why in TS plot this saturated vapor line heals towards the left. In PV plot it heals towards the left. This is because the specific volume decreased because of the compressibility. But here it is other way, that the specific entropy is reduced that you increase the pressure, and that way this curve heals towards left, and ultimately it creates a vapor dome meeting at a point known as the critical pressure. If we draw a constant pressure line like this, only in the liquid part I am doing, the critical pressure line is like this. So this is precisely this TS plot in the phase diagram. Now I come to this PT plot. Now to understand this PT plot very clearly, I think we should compare it with PV plot. That PV plot, this is the PV plot. I think you can see that is the PV plot. Now you see that here at any constant pressure, if you heat, this is the saturated solid, saturated liquid. Now here if you see, in this case what happens when the phase change takes place, these 2 points, 2 ends of the saturation state, solid and liquid. Similarly here liquid and vapor are spaced apart. This is because the specific volumes are different. We are placing it on V axis. They are same in pressure and temperature but vary in specific volumes. They are same in pressure and temperature, vary in specific volumes. For an example, if you consider this water. So this pressure 1 atmospheric pressure, this temperature 100 degrees Celsius, this temperature 100 degrees Celsius, but their specific volume varies. This temperature 0 degrees Celsius, this is 0 degrees Celsius, but their specific volume varies. But when you do it for PT plane, then two saturated states at the extreme 2 phases, they coincide to a point because they correspond to a single point with pressure and temperature. So similarly for the vaporization curve also, the 4, 5 point, they are the extreme ends of the 2 saturated point, they also coincide. So this curve is known as fusion curve, and this curve, all the points on this curve represent this mixture of solid and liquid, that means this zone. This part is the solid, this part is the solid, this is liquid, and again these points, that 4, 5 points, that 4 and 5, 4 dash, 5 dash, all these are on single curve. This is known as vaporization curve. Now the beauty is that this, if we draw this line, that is the solid liquid point on PT diagram at different pressures, we will see that this curve is very steep. That means the influence of pressure on the, if we consider the temperature, this temperature of solidification or melting is very less. Except for water, it has a positive slope. That means if you increase the pressure, the temperature for melting to the corresponding pressure, saturation temperature for melting or solidification increases very little. But for water, the behavior is little different. As you go on decreasing the pressure, the melting temperature or solidification temperature increases. But in both the cases, the decrease and increase is very slow, very small, so that this curve is very steep. This is the gift of the nature, so that these two curves meet at a point, whereas this curve is very flat, which means the pressure has a dominant influence on the vaporization temperature. That means this is the 1 atmospheric pressure, and if this temperature is 100 degrees Celsius, if we change the pressure to 10 atmospheric pressure, there will be a substantial change in the temperature for vaporization. So that this curve is relatively flat. Whereas for water it is not so, for melting it is not so. If it is 1 atmospheric pressure, if it melts at 0 degrees Celsius, if you change the pressure to 10 atmospheric pressure, so it will melt at a lower temperature. This is a peculiarity of water, but that lowering of temperature will be very small and very less than the 0 degrees Celsius. So this curve is very steep, whereas this curve is very flat, so that there is an opportunity that these two curves meet at a point. Okay, this point is the triple point. So below this point we straight have solid here and vapor here. You understand? I am giving an example. 1 atmospheric pressure, water is boiling at 100 degrees Celsius. If you go on reducing the pressure, the boiling temperature or saturation temperature goes on drastically decreasing. Whereas if you go on reducing this pressure on solid water, saturated solid water, or saturated water which is being solidified, or saturated solid water which is melting, this increase in temperature is very, very small, so that there is an opportunity where they meet at a point, and this point for water, the value of this point, I am telling triple point of water, yes, triple point of water, for water this value is, this PT is 0.00611 bar. You know bar, 10 to the power 5 pascals, and corresponding temperature is 0.01 degrees Celsius, 273.16. 273.15 is the conversion plus 273.15. So therefore 0.15. So therefore 273.16 K. So therefore you see, when you reduce the pressure from 1 atmosphere to this atmosphere, water boils at this temperature, and at the same time when you reduce the pressure from 1 atmospheric pressure to this pressure, that means this pressure, water also solidifies at this temperature. So that this is the meeting point. So below this pressure, if you heat a solid water, it will directly transfer into vapor. This process is known as sublimation. So therefore you see the saturation states in PT diagram appear at points, and the locus of that points are known as saturation curves. Fusion curve, this is vaporization curve. Clear? Now let us draw the HS diagram. HS diagram, if you draw, you will see that it will look like this. When you at a given, well, if you draw the HS diagram, enthalpy entropy diagram, it will look like this. I just first draw it. It will be little like same type of thing. It will be like this. Now when you increase the enthalpy, when you heat, for example, when you heat from 1 to 2, that means solid region, when you heat, both its enthalpy will increase at constant pressure, P is equal to constant. Again we think of a constant pressure heating, then what will happen? The pressure enthalpy will increase and entropy will increase. So qualitative trend will be like this. Now when we heat it at a constant pressure and temperature because of the phase change, this is solid plus liquid, this is liquid. Similar way, now we know this thing, that's why I am going little fast. So it is also increases, but it is a linear curve. Similarly in sensible heat part, there is an increasing trend, but when the phase change is there, this is linear. How we get this thing? Let us see that. In HS diagram at constant pressure, we know that dH is TdS plus VdP. Now at constant pressure, this is 0. So therefore dH del S, rather I can write del H del S, a very important relationship, is equal to T. That means at constant pressure, del H del S P is equal to T. That means the slope of a curve in HS plane at constant pressure, that means a constant pressure line in HS plane, the slope at constant pressure line in HS plane at any point is equal to the temperature of the system. Now when we go on heating at each and every point on sensible heating part, the temperatures are changing, increasing. So this curve is with increasing slope, steep. So if you draw this thing qualitatively like this, it will tell you that your concept is clear. Whereas when you draw this curve in this portion, it is constant. Why? Because T is constant. When phase change is taking place, each and every point T is constant during the phase change, solid to liquid or liquid to vapor. So that del H del SP is constant. That means it is linearly increasing. As you go on heating, both the enthalpy and entropy is changing. And if you draw another curve, constant pressure at a higher pressure, then this curve will have a greater slope. That means if you show this curve, linear curve in the phase change diagram, don't draw parallel to this. It is diverging type, because this slope of this curve is more than that, because this is equal to temperature. So saturation temperature is more than this. For example, this is 1 atmospheric curve. All these points corresponds to 100 degrees Celsius temperature. That means slope corresponds to this 100 degrees Celsius. Whereas if it is a 5 atmospheric pressure, if the saturation temperature is 150 degrees Celsius, that means this temperature is more. That means slope of this line, linear element, is more. So they are diverging in nature. Alright, this way we can construct the HS diagram. Now what we should do, we should compare these four diagrams. See that, very important. How do you compare? Compare means if you look, no question of comparisons, but if you look, then it will be clear. You see PV diagram. So I am only drawing the liquid, liquid vapor, and this is the liquid line. So this is liquid vapor. So these red lines are the constant pressure lines, whereas this line, these lines are the constant temperature lines, isothermal line. So if you want to understand the isothermal line, you see that at any point here, if you go on, move in this direction. What does it mean? That means at constant temperature, what are you doing? Moving in this direction means you are increasing the pressure. That means number of constant pressure lines intersects. That means if you move that an isothermal compression, you come to this point. That means you are coming to the liquid. That means compressing a gas, you can come to the liquid. That means, for example, this is the atmospheric pressure line. This is the atmospheric pressure line. This is the atmospheric pressure line. So this temperature is 100 degrees Celsius. So this is the saturation temperature. Now if this 100 degrees Celsius line extends here and you are at some point here, for example here, whose pressure is lower than the 1 atmospheric pressure, that means it is in vapor state. That means if you compress that vapor to 1 atmospheric pressure, then only it will become liquid, because 100 degrees Celsius water at subatmospheric pressure is a vapor. Okay. Similar is the case this intersection. That means this is 1 atmospheric pressure. Okay, and the corresponding isotherm is 100 degrees Celsius. This is 1 atmospheric pressure, but this is an isotherm at higher temperature. That means this is at a higher temperature, for example 150 degrees Celsius. If you compress it, that means it becomes at certain stage where this pressure will be the corresponding saturation pressure for this temperature, and it starts condensing. This is the liquid. So that's why the isotherms are like this, and this is coinciding with the constant pressure lines, and here the isotherms are very steep upward. Why? This is because if you make an isothermal compression, water is incompressible. There is a very little change in V. So these are the isotherms in PV plane. Similarly in TS plane, the isotherms are like that. We have already appreciated, and isobars are all like that. Isotherms are the lines parallel to S axis, and these points are the points, saturated points, and this gap is the change in the entropy. This is the PT point and this is the HS point, HS diagram. So these 4 diagrams, if you see at a time, then you see these points are the saturated point, these points as the saturated point. These points coincide here in PT, saturated point. Now one thing is clear, in saturated state, this point shows that pressure and temperature are interlinked. That means when you fix the pressure, temperature is automatically fixed. Now if you see the Gibbs phase rule, which we studied earlier, that Gibbs phase rule can tell you what is the number of independent variables required to fix the state of a system. That depends upon the number of components and the number of phases. So if you look that when the number of phases are 2, they exist in equilibrium, then the pressure and temperatures are uniquely connected. That means when pressure is fixed, temperature is fixed. That means only one variable is required to fix the state of the system. Okay, so they can, for example, liquid and vapor, they can coexist only in a pair of pressures and temperatures, not at all pressures and, for example, if this be the pressure here, so this has to be the temperature. Then only solid and liquid can coexist in equilibrium. So this be the temperature. So at this pressure, any other temperatures, either it will be vapor or it will be liquid. That means at a pair of pressures and temperatures, only the equilibrium between the 2 phases are possible. This is the TS, this is the HS. So these points are the saturated states. And here you see there is a change in the specific volume during this change of phase. There is a change in the entropy. There is a change in the enthalpy. That's why these points are spaced apart. But in PT diagram they are the points. So these points are known as saturated states. Now with respect to this, I will tell you what is known as subcooled, what is going to happen, subcooled or compressed and superheated and rarefied states. This is another concept. It should be clear that subcooled or compressed, they are the synonymous thing, or superheated and rarefied state. A very concrete example I have shown here. Let us consider the PV and the TS diagram. Now let us consider in PV diagram first this baseline pressure, that is 1 atmospheric pressure, this pressure line, 1 atmospheric pressure. If this be the 1 atmospheric pressure, the isotherm which coincides with 1 atmospheric pressure in the vapor dome, this is liquid plus vapor, that should be 100 degrees Celsius. That means this temperature is 100 degrees Celsius. That means if we have a liquid at, for example, 50 degrees Celsius, let us first locate here, that will be better. So correspondingly in TS diagram, let us consider that this is this similarly 1 atmospheric pressure line. So this is 1 atmospheric pressure line, and obviously this temperature is the 100 degrees Celsius. You follow clearly? Now if we have a 50 degrees Celsius water at 1 atmospheric pressure, so this point is here, that is known as subcooled liquid. Why subcooled? Because its temperature is lower than the saturation temperature corresponding to that pressure. At 1 atmospheric pressure, 100 degrees Celsius water is the saturated water for vaporization. That means the saturation temperature is 100 degree. It is below the saturation temperature 50 degrees Celsius. How can you show that? This you can show here. That means this lies on another isotherm which is at 50 degrees Celsius. This state is known as subcooled because this temperature is below the saturation temperature. And what is the degree of subcooling? That difference, 50 degree. At the same time, this is known as compressed state. Why a subcooled state is the compressed state? You can think from other angle that at this temperature, now if we want to, now at this temperature, if we want to vaporize this water, then what we have to do? We have to reduce the pressure. That means what will happen? So 50 degrees Celsius, that means if I now go like this, then we will see that this 50 degrees Celsius isotherm, that means if I follow this line, that means I am reducing the pressure. So if I go on reducing the pressure, there will be a point where this 50 degrees Celsius is saturation temperature, and that point the pressure is 0.12 atmosphere. This I have taken from the table. That means at 0.12 atmospheric pressure, water boils at 50 degrees Celsius. That means you can tell that this point is at a compressed state, that means at a higher pressure corresponding to the saturation pressure of its existing temperature. So that from that angle, this point is a compressed state. Clear? Compressed state. That means here it is at 50 degrees Celsius. So at 50 degrees Celsius, if you go like this, then it becomes the saturation state. So through that point, there is a constant pressure curve which is 0.12 atmospheric pressure. That means a subcooled state is a compressed state. This is because its temperature is lower than the saturation temperature corresponding to its existing pressure, or its pressure is higher than the saturation pressure corresponding to the existing temperature. So that's why a subcooled and compressed state, this is the subcooled or compressed state. Similarly, this is saturated state. Similarly, superheated state is a rarefied state. Let us consider at 1 atmospheric pressure a point here in the vapor region. Let this point is 150 degrees Celsius. This temperature is, that means we have steam at 150 degrees Celsius, 1 atmospheric pressure, superheated steam, and degree of superheat is 50 degree. Because it is 50 degree more than the saturation temperature, just the reverse of the subcooled state. So therefore, this is superheated. If you cool it at constant pressure, then it has to come to 100 degrees Celsius for condensation. So how to show this point here? This point here, this is the 1 atmospheric pressure. So you just extend this point and you see this cuts an isotherm, that is 1 at 1 p. That means we will have to extend this pressure line and the intersection of this pressure line with the 150 degrees Celsius line. This is the point here. So now if I want to, this is a superheated state. Similarly, this is a rarefied state. Why? Because if I have to condense this point, then what I have to do? I have to move in this direction. So when you move in this direction, you see that what you are doing, so you're at 150 degrees Celsius, that means you have to, at same, not in this direction, at the same temperature, if I have to now condense this, I have to move in this direction, so that it becomes saturated here. That means this pressure line is the higher pressure line, this pressure line is the higher pressure line, 5 atmospheric pressure line. That means this is 150 degrees Celsius, for which the 5 atmospheric pressure line is the saturated pressure. That means 150 degrees Celsius steam can be condensed if I increase the pressure to 5 atmospheric pressure. That means it is at a relatively lower pressure. That means it is at a rarefied state. That means its temperature is more than the saturation temperature corresponding to the existing pressure, or we can tell its pressure is lower than the saturation pressure corresponding to the existing temperature. It is clear. So that a superheated state is a rarefied state. Clear? So there are two states, subcooled or compressed state and superheated or rarefied state, where the sensible heating and cooling takes place. Now after this, I will tell you that we have seen in the in this diagram that this 4 diagrams, yes. These are the saturated states and the properties are well fixed, all fixed. That means this has got pressure, temperature, the same pressure, temperature, but other properties, specific volume of saturated liquid is fixed, specific volume of saturated vapor is fixed. This vapor is known as dry saturated vapor. That means completely dry vapor. Here the entropy is fixed, this entropy is fixed, this enthalpy is fixed, this enthalpy is fixed. But now question comes, what are these state points? What are these state points which shows different values of specific volume, specific entropy or even specific enthalpy, but at the same pressure and temperature, that means within the vapor dome. What the different points showing the different values of specific volume, showing the different values of specific entropy, showing the different values of specific enthalpy within the vapor dome, but at the same pressure and temperature indicate. They indicate physically a mixture of the two phase and the mixture composition is varying. For example, at this point it is full water. When you plot, when you go on in this direction, the point, this point is a mixture of water and vapor, and as you go in this direction the mixture composition, the vapor constituents increases, and here it is full of vapor. So therefore all these points are specified by a mixture composition, and all these points in the vapor dome represents a mixture of the two phase. That means in a container we may have both water and steam, but this mixture of water and steam, the composition varies, may vary, and that is represented by the state point. That means this is a pure component, this is a this is a single phase, this is a single phase. These are pure components, but these are a mixture of two phases. Clear? So therefore to specify any property for this point, these state points, we will have to specify the mixture composition, and that is known as dryness fraction. That is known as dryness fraction of a liquid vapor mixture. We consider here the steam and water. So with respect to the dryness fraction of steam, if we tell is a steam is equals to, that is denoted as X, which equals to the mass of dry vapor, steam or vapor, divided by the total mass, total mass of the mixture, which means the mass of dry vapor, let us denote mv, and total mass of the mixture, this is a mass of dry vapor plus the mass of the liquid, mf. That means at saturated liquid state, what is the value of x? At saturated liquid state, the value of x is 0. At saturated vapor state, the value of x is 1. This is sometimes known as quality of a vapor or quality of steam, quality of a vapor. That means x is equal to 0 is the saturated liquid line, x is equal to 1 is the saturated vapor line. It is clear? So therefore we can now, okay, now we can make different line like this, which are the, rather I will draw this here, let us. So now if we draw the PV diagram, if we draw the PV diagram like this, we draw the PV diagram like this. Now we draw the, only we are interested in the liquid plus vapor into vapor. Now this is C. Now you see at any pressure we have specific volume depending upon the value of x. So these are the liquid, these are the x is equal to 0 line. These are the, this is the x is equal to 0 line, and this is x is equal to 1 line, and in between we have different x. So we can draw locus of constant x with different values of x. So they all meet at critical point. This is x is equal to 1. Let this is x is equal to 0.9, it is x is equal to 0.6, x is equal to 0.3, finally x is equal to 0. Similar is the case for TS diagram also. We can denote the same way. We can show a TS diagram looks like this. Oh, sorry, diagram. However, does not matter. The scale is different. So TS diagram also. These are the constant pressure line. These are the constant pressure line. These are the constant pressure line. So that we can show different. Different dryness fraction points having various entropies, and we can draw the at different temperature or pressure lines. Sorry, these are all coinciding. Sorry, these are all coming from the same point. X is equal to 1, x is equal to 0, and various values of x. X is equal to 0.8, x is equal to 0.6, like that, x is equal to 0.3. These are the constant x curves, constant quality. Yes.
So what's the value of x at a critical point?
X at a critical point, I am telling you. That value of x at a critical point is a very interesting question. Just now I will explain it. What is a critical point? It's very difficult to understand what is the critical point. What is the value of x at critical point? Because all x values are meeting at the point. So what should be the value of the value of the x at critical point? The first answer is that the value of x is not defined at the critical point. This is the answer. The value of x, so geometrically all the constant x lines or different values emerge from critical point. So mathematically one can see that the value cannot be defined at critical point. So physically and both mathematically the answer is that value of x is not defined at the critical point. Very good question, I appreciate. Now in relation to that I will explain what is a critical point. So far we have studied the vapor dome, the phase diagram, how we can represent the state points in the phase diagram, in an isotherm, in an isobar, what is subcooled or compressed state, what is superheated or rarefied state. Now I will explain what is a critical point. Now you see that critical point is the point where the line, saturated liquid line and the saturated vapor line merges. You just follow these three diagrams, not in PT diagram. Now you see that when you increase the pressure in PV diagram, you see that the specific volume, the difference in specific volume is going to be reduced. Initially what happened, always we see the specific volumes of liquid is more than that of the vapor. But as you go on increasing the pressure, the difference between the specific volume of the liquid and the vapor is going to be reduced. And ultimately at C there is no change in the specific volume of liquid and vapor. First observation. Alright. Second observation, here in TS diagram you see the change in the entropy between these 2 points is going to be reduced. But before that it will be more appreciating that the change in the enthalpy between the 2 state points are going to be reduced. What does it mean physically? What is this change in enthalpy imply? The heat added to this. That means if you write the steady flow energy equation, you see enthalpy of this dry vapor minus enthalpy of the liquid is the amount of heat added. Specific enthalpy difference is the amount of heat added per unit mass. That means this is precisely the latent heat. That means as you go on increasing the pressure, the latent heat is reduced. That means the vapor enthalpy and liquid enthalpy are coming close together. That means it requires a very less heat to become the vapor, and ultimately at the critical point it becomes 0. That means from this 3 diagram we see obviously the entropy change is 0. That means at critical point the conclusion is that the properties of the liquid and the properties of the vapor, disaturated vapor, disaturated liquid become exactly the same, and liquid does not take any heat to vaporize. What does it mean? It means that except the critical point, that means below the critical point, not except below the critical point, what happens? There is a distinct phase transition. That means when an experimental does the experiment, he sees that when he gives the heat to water, sensible after taking sensible heat at a constant pressure, it attains a temperature. And clearly he sees that at that temperature, there is a time when the liquid is getting converted to a vapor. And how do you know that it is going from a very dense medium to a very light and rarefied medium, which we distinguish as vapor? And it takes some time. That is because it takes some finite amount of heat, which is the latent heat. And if he measures the properties like specific volume, enthalpy, entropy, internal energy, you will see there is a finite change in that property. So therefore the phase change process is defined, well defined, where there are 2 distinct phases and there is a time taken for a given amount of a particular phase is to be converted to other phase having different properties from the earlier phase, okay, and taking some finite amount of it known as latent heat. But at critical point, all these differences are zero. There is no difference. That means if you go on heating at the critical pressure, if you go on heating now here at critical pressure, for example here, if you go on heating water like this, if you go on heating water like this at the same critical pressure, you will see slowly water is heated, and what happens at this some temperature it is defined here where automatically it is flashes into vapor. This is the language which a book uses. It automatically flashes into vapor. Very difficult to understand. What does it mean? Near that temperature, physically thing is like that. Slowly the density of the water, for example, if you think in terms of the density, one property, specific volume for example, specific volume slowly and gradually changes and there is no discontinuity. Slowly transfer. That means it is very difficult to recognize liquid from vapor in a distinct transition zone. You understand? The specific volume is slowly increasing and there is a smooth transition and you cannot distinguish from one distinct state of the phase to another distinct state of the phase. It is a continuously increasing function or a continuously decreasing function. It is very difficult to tell that this is the point before which there is a distinct phase, after which there is another distinct phase. This we define below the critical point because there was a discontinuity. If you plot the specific volume versus time, then temperature, then you will see at a constant temperature, the specific volume there is a sudden jump. You understand? For an enthalpy there is a sudden jump. There is a discontinuity, but there is no discontinuity. That means liquid automatically converts into vapor. This is the book definition, but I will tell you, we should not define anything like that. There is no distinction between liquid and vapor. Critical point of a component like that, that means they remain as a component. So there is no distinction between liquid and vapor in the critical point. Critical point, for example, at same isotherm, if you go and compress the vapor here, if you follow, you go on compressing the vapor with this, that means the specific volume is decreasing and it continuously goes on decreasing. But here if you do, specific volume is decreased and here you see at the same temperature there is a drastic change in specific volume. There is a discontinuity while the temperature remains the same. You understand? That means we can define two distinct phases at critical point, beyond the critical point, at and beyond the critical point there is no distinction between the two phases. Absolutely there is no distinction between the two phases. One phase automatically transferred to other phase, the books write, but there is no such phase. It is the, for example, water. At critical point, if you define above critical pressure, water at this temperature, water at that temperature, having a property of this, having a property of that, but there is no distinction at all. Now I tell you the values like that. For example, you can understand better critical properties, critical parameter rather you write, critical parameter of water. This is an information many of you know that PC is 221 bar, approximate values. I am not going for the decimal point. TC is 374 degrees Celsius and VC is 0.003 15 degrees Celsius, like a meter cube per kg.
Sir, TC should be Kelvin.
Okay, you can give it in Kelvin, but you can express in TC Celsius also, does not matter, Kelvin you can
374 Kelvin.
no, 374 degrees Celsius, not the Kelvin. When I am writing Celsius, it is Celsius, not the Kelvin, not at all. You can convert it into Kelvin by adding 273. But sometimes this is the conventional value, so usually we give it terms of the say Celsius. Okay. Now see, try to understand what is the physical concept. That means if one tells, again I am coming here, that at this point and this point, what is the difference? This value is greater than 374 degrees Celsius. This value is less than that, less than 200 degrees Celsius. But the pressure is 221 bar or even at a higher pressure. That means at pressure at PC greater than is equal to 221 bar, H2O greater than 374 degrees Celsius or even equal to H2O and less, it is not wise. I am telling, this is the concept, many books do not make it so clear. It is wise to tell, not to tell that whether this is liquid or, that means this is liquid, this is vapor, no. This is water at below 374 degrees Celsius, water above 374 degrees Celsius. Has definite properties, it has definite properties. So there is no distinction between liquid and gas. You understand this thing? But on the other hand, if P is equal to 5 atmospheric pressure, H2O at 200 degrees Celsius, H2O at 100 degrees Celsius, then people will tell, oh, this is steam, vapor, and this is liquid, water. Though this has definite properties, this has definite properties. Why? Because when you go from this to this at this atmospheric pressure, then there is a transition, phase transition. But at critical point, there is no phase transition. Beyond the critical point, there is no phase transition. System is unique by its component. So critical point, what he asked the question, the definition of phase change, identification of phases, all these things are not valid. Clear? Many books write many languages. I am telling you firmly, these are confusing. That liquid automatically converts into vapor. What does it mean? There is no difference. If an experimenter sees that, it is very difficult for him to tell, oh yes, here is the discontinuity. When a liquid is being boiled and going to vapor, how do you distinguish? A layman, because he distinguishes from a specific volume. There is a dense medium, there is a light. You tell this is a vapor and this is a liquid. But if it goes on continuously changing without any discontinuity in a specific volume, no experimenter can tell, yes, this is the point where I tell a particular phase is being converted to another phase. Below this point, this is a different phase. Beyond this point, that is a different phase. No difference. No latent heat is required. That means, again and again I am telling that the phase transition is not defined at and above the critical point. It's clear? Okay, I will be very happy. Because these are very important things. I tell you, these concepts are very much related to, actually you know that these cryogenic applications, cryogenic rocket engines or other, where the liquid oxygens are used at more than critical conditions and they are vaporized. So there is no distinct phase for that. When we do the calculations for heat transfer and other things, we try to recognize this, that there is no such continuous change of phase. There are many applications where liquid is used above the critical points, that is above the critical pressure, heating of the liquid or cooling of the liquid take place. There itself liquid as it is, that means it is recognized by its component only, there is no distinct phase transition. Okay, now very important things for come down to the reality, that we know that at any intermediate points the composition is specified by X. Okay? The composition is specified by X, that is dry vapor divided by dry vapor plus fluid. So therefore, the extensive and also the corresponding intensive properties depend on this. Intensive property corresponding means specific extensive properties. Extensive properties are the properties which depend on the mass, and therefore in a mixture of two phase, the extensive property will depend upon the composition. If I ask you what is the what is the internal energy, enthalpy or entropy of a mixture of water and steam at a particular pressure and temperature, you will ask me, tell me the composition, then only I will tell, because I know these values for this steam, dry steam at that pressure and temperature, because this end of the curve. I know this value for the saturated liquid at that pressure and temperature. But if you tell a mixture of that, then you tell me the value of X, then I will tell you, and this is simply a class 4-5 level calculations, that if you define that, I think you can write immediately all such properties, specific internal energy for any quality or dryness fraction X is what? 1 minus X. Now before that I tell you, this F is the conventionally used subscript denoting the properties at saturated liquid states, and G is the conventionally used subscript to denote the properties at dry vapor. So therefore it will be X into Ug. I think there is no disagreement with that. It is simply a primary school job. So specific enthalpy, that means if I know, that means this is the contribution from liquid side and this is the contribution from the vapor side, dry vapor side. Similarly S, that means all intensive property corresponding to the extensive properties, that means these are specific internal energy, specific enthalpy, specific entropy. So this is, that means if I know the values of these properties, specific internal energy, enthalpy, specific entropy at two saturated state points of the two phase, then I can find out the values for a mixture of these two specified by x. So I require another one parameter, more parameter x to determine this. All right. So this is a very important thing. Now I tell you, there is a table for, there are tables for all these properties at saturated state, end states, and also in the vapor, superheated vapor region, and also in the subcooled state for each and every substance. But for our work, we are much more interested for all common work with water. Water is a very common fluid which are used in practice while its phase changes. It's very common example is the steam power plant. So that table which tabulate the properties at saturated states and also the superheated, rarefied or compressed subcooled state are known as, for water, steam tables. Okay. So I think you develop practice in your house to see these steam tables. I tell you how does it look like. Again, it is a primary school level education, but you must know that a steam table documents the thing this way, that there are two type of steam table. One is the steam tables for saturated steams, steam tables for saturated steam, and this table is made two ways. One way is the pressure as the left column, that means it goes on writing the pressure from very low value, goes tabulating the pressure, then the corresponding saturation temperature. For example, if I am giving pressure is the 0.1 megapascal, which is the atmospheric pressure, almost equal to atmospheric pressure, then the corresponding saturation temperature is 99.63. Then they tabulate specific volume Vf in meter cube per kg, specific volume Vg centimeter cube per kg, sorry, because otherwise what happens, if you put it in the same unit, there has to be some 10 to the power minus 3 or like that. So sometimes the units are changed. This is centimeter cube per kg is a typical value, 0.1. So this is the specific volume for the liquid, specific volume for the dry vapor. This is the value corresponding to this pressure for water. Then specific enthalpy for liquid, saturated for saturated dry vapor. Similarly, the specific entropy for liquid and specific entropy for saturated vapor. Clear? This is a typical value for 0.1 megapascal. Now the pertinent question comes, I know many of you are eager to ask that how do you calculate this value? Chandrasekhar, what is your question? Do you have any question? How do you calculate this value? Why not? So that means you must know the reference. If I give you a table, look, depending upon these are the location, this is the value of the potential energy. That means you have to ask me that what is the datum. So whenever I give and assign a value of the enthalpy, value of the entropy, similarly the value of the, oh, one thing is missing. I am sorry. What is missing? Internal energy. Very good. Internal, because this is such a short paper, internal, and to write internal energy. Similarly, there will be UF, UG. Sometimes in many steam tables the difference is also written. For example, HFG. HFG has got a very much physical significance, that is the latent heat. Sometimes they give VFG, they give UFG, that is Vg minus Vf, that means the change in the specific volume. Usually Vg is much higher than Vf, Ug minus Uf. So I am sorry. So these values also are not there. So this way saturated steam tables are generated. So what are the references? That means I have to know the reference datum where from these values have been calculated. The reference value is like this: saturated water at 0.01 degrees Celsius means pressure is, that means it is triple point, pressure is 0.00611 bar. That means this is the saturated water at this temperature, means which pressure is this. That means water at this temperature and pressure is saturated. That means it can convert it to vapor. At the same time, if you extract heat, it will convert to ice. That means it is a triple point. Triple point, both the three phases exist into equilibrium. So what we learned, that two phases can exist into equilibrium at several states. But these states have a restriction that pressure and temperatures are not independent, they are dependent. If pressure is fixed, temperature is fixed. So there may be many states, but with coupled values of pressure and temperatures. But in triple point, the state is uniquely fixed, that is only unique state. So three phases can exist in equilibrium only at single phase. That comes from the Gibbs phase rule also, I will tell that. So at this saturated water condition, that means triple point, this is typically the triple point. I am going probably a little fast, I don't know. If you have got any doubt, you can ask me question. Triple point, we consider the internal energy is 0. H a small value, H is 0 plus PV. So question comes with the internal energy, because we know from the beginning of the thermodynamics, the internal energy is introduced in terms of its difference. The way potential energy changes, in terms of its difference, gravitational potential energy, always it is defined in physics in terms of its difference. So therefore U is 0, that means U absolute value, to designate the absolute value of U at a state point, you require a reference U. Similarly, what are other things? Entropy, entropy is also 0. That means internal energy, entropy are made 0 at this condition. Okay. Now Gibbs phase rule, if you remember, F is equal to, I have forgotten the nomenclature which I used earlier, is C minus R plus 2. What is C? C is the number of components, R is the number of phases. So now you see, if the number of the component is 1 and phase is 2, then this F is equal to 1. That means two phase system, the variance is 1. That means if one parameter is fixed, intensive property, state is fixed. That means if you tell that steam air coexisting equilibrium at 1 atmospheric pressure, enough is told. That means sufficient condition is told. Science does not require more things. So 1 atmospheric pressure means everything is known. 100 degrees Celsius, corresponding volume, corresponding what is called enthalpy, internal energy, everything is. Or you tell the steam or water system existing at equilibrium at 100 degrees Celsius, enough. That means only one parameter is required. If it is a triple point, what is F? Tell me 1C, this is 3. So therefore that is 0. That means for triple point state, variance is 0. Triple point state, variance is 0. That means triple point is a unique state. We cannot have any variance. For all substance, there is a unique state where the three phases of the substance coexist in equilibrium. That is the triple point. Okay, clear? So with this thing, we we tabulate the values which are documented in the steam table. Now when superheated steam table, this is for saturated steam tables. Superheated steam table, again I tell the saturated steam table, with pressure you get temperatures corresponding the value, specific volume, internal energy, specific enthalpy, specific entropy. These tables are made in two ways. One, pressure here corresponding temperature, another temperature wise corresponding pressure. For that what happens is that the interpolation job is little bit easy. You don't have to much interpolate. Sometimes you require at some temperature, so you have to find out what is the saturation pressure. Then you see the temperature table. That depends upon, if I tell that water and steam at 150 degrees Celsius coexisting in equilibrium. If there is a pressure table, you may not have 150 degrees Celsius here, so you have to interpolate. So you see temperature wise, there you will see that 150 degrees Celsius. And the resolution between the two pressures and temperatures are usually 20 degree, 50 degree depending upon the table. Okay, clear? So left side pressure or left side temperature, corresponding saturation temperature or saturation pressure, and all the values of specific volume, specific enthalpy, specific entropy for two endpoints, that means two saturated states. Clear? For superheated steam table, the documentation is made like that, but you have to look the steam table and have to develop practice while solving problem, which I will do in the next class. Superheated steam table, what they do? Now in a superheated state, you know, for a given pressure there may be number of temperatures. For example, 1 atmospheric pressure, steam may exist at any temperature, starting from 100 degree, 150, 120, 300, doesn't matter until and unless it goes to the plasma state. So therefore at a given pressure, it starts like that. On the top, it writes the saturation temperature corresponding to that pressure. Then it starts like that, it tabulates specific volume, internal energy, enthalpy and entropy of the superheated vapor at that state. First they tabulate saturated state. This is the saturated state values, which is the values which will coincide with the values for the dry vapor in the saturated steam table. Then they tabulate with different temperature this. That means if you want to find out the properties of superheated steam at 250 degrees Celsius, you see this. And go on 500 degrees Celsius and all this. up to certain limit. That limit depends upon our usable working range. Clear? Okay.